In this section, we're going to learn more about derivatives. First, let's talk about how a derivative is a rate of change. So we've been referring to the derivative as the slope, and that's one interpretation of it. But along with slope, if you think about it, slope itself tells you how fast the function is changing. Okay, and this is actually very important application of derivatives that also comes into play even if we're not thinking about it geometrically with slope. So if you think about things like slope equals rise over run. Okay, or if you thought about it back in your previous math classes, you might have said if x goes up 1, y goes up how much? And in this case it would be, let's say, m for your slope. And I'm just saying m so I can put something there. So if x goes up 1, then y goes up m. That's the definition of slope. So let's come and look at our example. If f of x equals 3x squared, let's first find the derivative of f evaluated at 10. So f prime of x, let's find the derivative first. Using our power rules, we can say, okay, the 3 gets to stay there. That's just a coefficient. Now the power of 2, it comes down to multiply, and then you drop your power by 1. So we just get 6x. So f prime evaluated at 10 is going to be 6 times 10, or 60. So what does this mean? So this means that at x equals 10, now specifically it's at x equals 10 because my derivative is changing constantly. So my slope changes constantly. But this means around or at or around x equals 10. If x goes up 1, y goes up our slope, which is 60. So that's what our rate of change tells us. So again, if x goes up 1, y is going to go up 60 because our slope at that point is 60. Now we'll apply this again in our next example. But our next example now brings in some economics terms. Okay, so first we learn about cost. Okay. So cost is what it costs the company to make and sell X items. We label that C of X, so you can remember as cost. Revenue is the amount of money the company actually gets for selling X items. So that's the money coming in. So you can think about it, if you prefer, money out for cost, money in for revenue. Okay. Profit, P of X then, is the difference between the money that comes in and the money that goes out. So it's the difference between the money a company gets and how much the company had to spend. So the profit is always R of X minus C of X. You're going to use that for the rest of the semester. You need to know these three things and know that profit is revenue minus cost. Now in this section we do introduce a new term which is called marginal. And we use this for our economic terms, and basically it just means the rate of change. So if you wanted to say find the marginal cost means how fast is cost changing, so you take the derivative of cost. So marginal cost means how fast is the cost changing. So to look at an example, if the cost of producing X items, if C of X is 0.5x cubed plus 28x plus 500. Let's find, okay, we are not finding the marginal cost yet. We're kind of building up to it. Let's find the actual extra cost of increasing production from 30 to 31 units. So to do this, you say, okay, well, how much does it cost to produce 31 units? And you plug 31 into this equation. So 0.5 times 31 cubed plus 28 times 31 plus 500 equals 16,263.5. So that's the cost of producing 31 units. The cost of producing 30 units is you do the exact same thing but put in a 30 into your equation. Which is 14,840. So the actual cost of increasing from 30 to 31 units is you do what? 31 units minus 30 units. So 16,263.5 minus 14,840 gives me 1,423 $30.50. So again, this is the actual difference if you go from 30 units to 31 units. You should just find the actual cost and find the difference. Okay, so that makes sense, something we could have done before calculus. Now though, let's find the marginal cost when x equals 30. So marginal cost means find the derivative. So first you find the derivative, the general derivative. Okay, so you can only look, this 0.5 gets to stay there, times, now you bring down the power of 3, and then you drop your power by 1, so 3 minus 1 is 2. Plus 28, now if you're not sure how to find the derivative of 28x, remember x is like it's to the power of 1, because you can always say that something is to the power of 1 without changing it. So the 28 stays there, bring down the times the power of 1, and drop your power by 1, which will put you out as 0. Plus 500, what's the derivative of a constant? The derivative of a constant is always 0. So we have 0.5 times 3 is 1.5 x squared plus 28, because x to the power of 0 is just 1. So that's our derivative. So our derivative at 30 equals 1.5 times 30 squared plus 28, which is 1,378. So what does this mean? What does marginal cost mean? This means if x equals 30, then if you increase by 1 unit, the cost should increase by about 1,378. Now, why is this only an about and not an exact? Okay. The reason it's about is if you were to graph the actual cost function, it would look something like this. So here's my 30, here's my 31. That's not an exact straight line in between, and so it is still only an about, okay, because you kind of have a bit of a curve in there, so it's not going to be exact. Okay, so we found the difference in the actual cost. We found our marginal cost, which is saying, okay, if x is 30, if you increase by about 1 unit, your cost should increase by about 1,300. Let's then use that to estimate the cost of producing 31 items. So to do that, you'd say, okay, well, C of 30, which we found up above, is 14,840. And if we go up 1 unit, cost should go up about 1,378. So we are going to predict or estimate that C of 31 will be our 14,840 plus how much we think it should go up by, which is 16,218. So this was our estimate. Our true value was 16,263. So they are still very close. Okay, we're only off by about $40 or so, less than $100. And again, it's not exact because you're on a curve and not straight lines. Okay, now our textbook has very official formulas for this. They're saying that the derivative of A is approximately equal to the difference in cost between A and A plus 1. Or they're saying C prime of 30 is about the same as C31 minus C of 30. This sounds very formal. They write this out for cost, they write out for profit and revenue. You don't need to memorize these formulas. Instead, you should just remember, what does the derivative mean? The derivative always means if you go up by 1x, y should go up by blank, whatever you get for your derivative. And from that, you can do all the problems without actually messing with complicated looking formulas. So, new topic now. Let's learn how to do the derivative of just one variable. Okay. So sometimes you're going to get functions that have more than one variable, but we still want to be able to take the derivative. So here's an example. The profits of an imaginary company can be modeled by this function I just made up to demonstrate with. So the profits, P of x, well, not x here because we have multiple variables, just P, is 5.2 s to the power of 5 minus 3.2 l squared minus a minus 21 times m times l cubed plus 40 cubed. Looks very complicated. It's probably actually simple for real life. Where S is sales, L is labor, A is advertising, and M is materials. So if you think about it, it makes sense that your profit is not going to depend on just how many you sell, but you're also going to have to talk about different things like sales and labor, etc. But sometimes we still want to take the derivative, or maybe we're only interested in one variable specifically. Okay, so in this case, we want to look at the marginal profit. Okay, so we want to see how fast does profit change. But we can only take the derivative with respect to one variable at a time. So you pick one variable you're interested in. So for example, what would be the marginal profit with respect to sales? So this is the variable that we actually care about. So our variable of interest. Not that we don't care about the others, but we can only focus on one at a time. So it's the marginal profit with respect to sales if we have 10 sales. So first we'll have to take the derivative of the function p with respect to s. And we write this as this dp over ds. We put the s on the bottom to tell us that we're taking the derivative with respect to s. And so if we want to take the derivative with respect to just one variable, this is the key thing. You treat every other variable as if it were a constant. A constant means just a number. So you can even plug in a number if you really want to, as long as you remember what it is. So you treat every other variable as if it was a constant. So the derivative of p with respect to s. So you come back up to look at your p. So let's do this part first. 5.2 times s squared. Well, that has an s. That's the variable I'm interested in. So let's do that derivative as normal. So the 5.2 is there, and you bring down the power of 5, put your s in, and drop your power by 1. Okay, next piece. Now we have minus 3.2 l squared. Now L is not the variable we care about, so we treat that as a constant. And what's the derivative of a constant? The derivative of a constant is 0. Minus A, again, we don't care about an A, so it's just a constant, so 0. Minus 21 times m times l cubed plus 40 times 3. Notice there are no s's there at all, so it's still just a constant, even though it's very complicated looking, and it's still just 0. Okay, so you put all this into your calculator, you get 26 s to the power of 4. Okay, then how do you plug in the 4? We have this nice fancy notation, so the derivative of p with respect to s, and sometimes we'll write it like this. We'll say evaluated at, not x, but s in this case. That means our derivative when s equals 10. So our derivative of p with respect to s when s equals 10 is going to be just plug in your 10. $260,000. So the marginal profit with respect to sales when sales equals 10 is $260,000. Oops, I didn't need to type that, did I? So marginal profit with respect to sales for 10 sales is $260,000. What does this mean? So remember, again, derivatives are just slope, which just tells us the rate of change. So if x goes up 1, y goes up 260,000. So, or in this case, when we start by making 10 sales, because that's where we are in the curve, we can expect that if we make one more sale, our profit will go up by about 260,000. So we're making a very big profit on this item. Okay, so remember it says if x, or in this case s, goes up by 1, p goes up by 260,000. It's just the basic definition of slope of rise over run. Okay, now let's make it more complicated. Let's try and find the derivative of p with respect to L. So now we care about L, or labor. So again, to do this, you're going to remember that everything but L is like a constant. Again, sometimes people, I tell them just put a number like a 7 in there and see what you do for that, and then go back and change it back to what it's supposed to be. But the derivative of p with respect to L. So this 5.2 as the fifth, that doesn't have any L's, so it's just a constant, it's just 0. Minus, now 3.2 L squared. We do care about the L, so we'll do 3.2, you bring down the power of 2, and you drop the power by 1, so from 2 to 1. Okay, minus, now A, that doesn't have any L's, we don't care about it. Minus 21 times this m times L cubed plus 40 raised to R3. Notice I already put a box around it. That's so we can do our general power rule, or our chain rule. To do this, because it does have an L in, we don't have to worry about it. You take the derivative of the outside. Remember, these are our box rules. So we'll do 21 times, and keep everything inside the box the same. Okay. Oops, I didn't leave enough room there. Sorry, minus 21. So you bring down the power of 3, you times it, you keep everything inside the box exactly the same, and you drop the power from 3 to a 2. Okay, now you times it by the derivative of what's inside the box. So m times L cubed. That m is just any other constant. It's not a variable we care about, so it's just like a constant. If it was a 7, we would just leave it there, so we just leave it there. You bring down the 3 from the L cubed, L, and write it as the power of 2. Plus the derivative of 40 is 0. Okay, so again, this was our general power rule we just learned about in the last section. So this is the derivative of the outside, and this is the derivative of the inside. So we do have a fair amount of simplifying to do. We get negative 6.4 L minus 189 times L, m times L squared times m times L cubed plus 40 squared. Okay, again, what you remember here is just only look at the variable you care about, treat everything else like it's a constant. And finally, second derivatives. Our second derivative we can write as f double prime of x, or we write our derivatives like d over dx, but we put a 2 on the d and the x. And really, to take a second derivative, it's very, very simple. Okay, you take the derivative, simplify, and then take the derivative again. That's what a second derivative means. So if f of x is 3x squared minus 5x plus 3, let's find the second derivative. So first, you find the first derivative. So 3x squared, you have your 3, you bring down your 2, x, drop your power by 1. Minus 5x, you can think of this as a 5 times x to the power of 1. So 5 times 1 times x to the power of 0, plus m3, the derivative of a 3 is just 0. Simplify 6x minus 5, because x to the power of 0 is just 1. Once you've done that, now you start completely over and just take the derivative like you normally would. Absolutely nothing special. The derivative of 6x is 6, derivative of 5 is 0. So, 6. See, truly nothing simple on the complicated on this, you just take the derivative twice. Let's try this next example. We want to find the second derivative. This means find the second derivative of the square root of 5x plus 3. Now I'm going to rewrite this as 5x plus 3 to the power of 1/2, just because it makes my life a little bit simpler. Okay, again, this kind of comes back down to our general power rule. We're going to need to put a box around it and do derivative of outside times derivative of inside. So first, you write down, I want to take the derivative once. And this notation is a little bit more clunky. So to take the derivative the first time, you say, okay, bring down the power of 1/2, keep everything inside the box exactly the same. So there's my box, and drop your power by 1. So 1/2 minus 1 is negative 1/2. Times, and now you do the derivative of what's on the inside. So derivative of 5x plus 3 would be 5. Simplify this, it's going to be 5/2 times 5x plus 3 to the negative 1/2. Again, this was derivative of outside. This is derivative of inside. So derivative inside, derivative of outside. Okay, so we found our first derivative. Now, we take the derivative of that again. So the derivative of 5/2 times 5x plus 3 to the negative 1/2. Okay. So again, here's my little box around the inside. We're going to do derivative of outside. So the 5/2 stays there, times it by our negative 1/2. Keep everything inside the box the same, and drop your power by 1. So 1/2 minus 1 is negative 3/2. Times it by the derivative of what's inside the box, which is just 5. So outside, inside. So my final answer, our second derivative of our square root of 5x plus 3 is, let's simplify that, so 5 times 5/2 times negative 1/2, so let's see, that should be negative 25 over 4 times 5x plus 3 to the 3/2.